Good morning, everyone. Welcome to the San Francisco Summit. First time, I think, for a lot of us to be at one of these in person, so it's nice this year. My name is Andy Katz. I'm a product manager with AWS. I'm going to talk to you today about new innovations in Amazon RDS in 2022. So a lot of things have happened in the last year, more recently in the last 6 months. Give you an overview of these things that have come our way. So there are 5 things I want to talk about today. I'll talk about new database instance types. We've had something of a Cambrian explosion in instance availability on Amazon RDS. We'll talk about those and when and how to use them. New innovations for MariaDB. We've invested a lot in Amazon RDS for MariaDB, and there's a lot of new features and capabilities on that engine we'll talk about. For those folks who build on containers, we'll talk about RDS and Kubernetes playing nice. A new service that launched at reInvent last year called Amazon RDS Custom for customers that need more access to the host when they're deploying their applications on a managed database. And then finally, a new high availability capability for open source databases on Amazon RDS, multi-ZDB clusters. So first, some background. For those that are unfamiliar, Amazon Relational Database Service is a fully managed relational database service with your choice of up to 7 database engines, including open source engines like MySQL, Postgres, MariaDB, and commercial engines like Oracle and SQL Server, as well as Amazon's own bespoke database, Amazon Aurora, which has wire compatibility with Postgres and MySQL. Now today we're going to focus on 5. We'll focus on the bit-for-bit community open source engines and SQL Server and Oracle. So we'll start with new instance types. So we have a bunch of new instances that are designed to support different workloads. So in the past year, in rough chronological order, you'll have seen the introduction of R5B instances, which has 3 times faster IOPS to EBS volumes for IO-intensive workloads. This is particularly useful for customers using RDS for Oracle or RDS for SQL Server. We've introduced X2G instances for even more memory for high memory workloads. We'll talk about that more in depth in a little bit. For those that have burstable workloads, where you don't need the database cranking continuously, we have burstable instances, the latest of which is the T4G Graviton-based burstable instances, useful for dev tests and gives you better price performance than the previous generation. We've introduced instance types with local storage. We'll talk about how we take advantage of that in multi-ZDB clusters later in the talk, but that gives you one example of faster write transactions. And most recently, we've introduced the next generation x86 instances, M6i and R6i, for SQL Server and Oracle. And those came available recently, and you can try them out today. Now, I want to talk a little bit about X2G instances, because a lot of database workloads are memory constrained. They don't need the CPU, but they need more RAM, so they have a bigger working set in memory. And the M type and R type give you increased memory. R gives you double the memory per core of an M. But it turns out that X2G gives you double the memory of an R. And there's something that people don't realize, which is when you think about scaling your workload vertically and you're running on an R5 24x large, you say, well, where's more memory when I need it? And it turns out by going to an X2G 16x large, you can actually get more memory. You have a terabyte of memory on that instance for those memory-bound workloads. And yes, you have fewer cores, but in a memory-bound workload, you typically don't need those cores because it's memory that's constraining your workload, not CPU. And so there is headroom when you have a memory-constrained workload, and it's just a counterintuitive movement from the 24XL to the 16XL by going from the R family to the X2G family. Now let's talk a little bit about MariaDB. We made a lot of enhancements to MariaDB in the last year. Most recently, all these arrived with MariaDB major version 10.6. I want to talk to you today in depth about delayed replication, the MyRock storage engine being added to MariaDB as an alternative, multi-major version upgrades, and IAM integration with MariaDB. So we'll hit this set. So let's start with delayed replication. Delayed replication is useful in disaster recovery scenarios. So you set one of your read replicas to lag behind the primary by a set amount of time, and you can configure that. Now, why do this? Well, imagine somebody fat fingers the database and corrupts a table, deletes a table, drops a table, and you say, I wish we hadn't done that. Instead of having to go and dig out your backup and take the time to restore the database, you can instead stop replication of that read replica and promote it to your new primary. And so it's a faster recovery motion than using backup. So in situations where you're worried about something like this happening for any reason, this is a way to have faster recovery in a disaster scenario. And the whole thing is configured using stored procedures. Now we've also added the option of the MyRock storage engine from MariaDB. So today, you deploy MariaDB, you get the InnoDB engine. That's the same storage engine that's also used with MySQL. MyRocks is an alternative. MariaDB supports different storage engines, and this adds the RocksDB capability to MySQL, which is really well suited for write-intensive workloads. And so MyRocks achieves this by giving you greater space utilization. So it packs the data on the disk more efficiently. It writes faster, it replicates faster, and your data loads faster. So if you have a database that's write-intensive, needs a performance boost, MyRocksDB storage engine from MariaDB is a good choice. We've also added to MariaDB multi-major version engine upgrades. This is something folks using RDS for Postgres have enjoyed for a while, but essentially what this lets you do is go from an older major to a newer major version in one step, rather than having to do it sequentially, major version by major version. So for example, MariaDB 10.2, 3, 4, and 5 can all be upgraded to MariaDB 10.6 in one step. And these are major versions of MariaDB for the folks who are not familiar with MariaDB. And so that saves you time, because there's a single migration path instead of having to do several hops to get to the latest version of MariaDB. And we've added AWS IAM integration with MariaDB, so that now you can have fine-grained access control of who can get to the database, which services under which conditions, and set least privileged access to the database in your applications, and control it from a central location. And this is supported as part of MariaDB 10.6, minor version 5, and higher. That's MariaDB. We'll move on now to talking about containers. I'm curious, in the room, how many folks build on containers, possibly with Kubernetes? So I'm seeing third to half of the group. So we'll tell a story of a developer, Anna. Anna has a dilemma. She's a web developer. And she deploys her applications on Kubernetes, and her application was originally built with SQLite, but she's outgrown it. Self-managing a relational database in Kubernetes is not really how she wants to spend her time. Amazon RDS offers this choice of managed relational databases, but that means Anna can't create and manage that database from within her Kubernetes API. Until one day, we released AWS Controllers for Kubernetes for RDS. I know it's a mouthful. ACK for RDS is shorter. Essentially what this does is allows you to manage Amazon RDS databases, all 7, using the Kubernetes API. So what you see on the left looks very different than a typical CLI command for launching a DB instance on Amazon RDS. And that's because it's a Kubernetes manifest. And this manifest, when you have the ACK controllers on your cluster, through kubectl apply, you can spin up an RDS database. This is an open source initiative. You can see the link below, and it enables GitOps and other kinds of workflows and tooling with your Kubernetes clusters. And it's as straightforward as, for example, you change one line at the bottom here. You see multi-AZ is true. ACK will then convert your database from a single AZ to a multi-AZ for high availability in your cluster. And again, it makes the endpoint discoverable. It makes it easy to manage the database all through using the Kubernetes API. So now I'll talk about something a little more challenging and different. Amazon RDS Custom. So Amazon RDS Custom is really to allow you to run legacy, custom, and packaged applications on a managed database service like Amazon RDS. And so the way to think about this is today, Amazon RDS takes care of everything but the application layer. It manages the scaling, the availability, backups, patching, OS installation, the hardware, everything is managed for you by Amazon RDS. However, Amazon RDS restricts access to the host. That's how we keep the service secure and make it highly available for our customers. So the alternative is you can manage everything yourself on EC2, except with hardware, which is managed for you by EC2. What Amazon RDS Customs gives you the middle ground, which is it fills the gap between self-managing and a fully managed Amazon RDS database. It allows you to customize the underlying OS, the database, and the infrastructure around it for those applications that require things like root access to configure the application. But once that's done, it automates the setup, monitoring, and maintenance of that relational database. So you can decide how much access you want to have on the root. And so what this looks like in practice, this is an example for SQL Server, is you create an RDS Custom for SQL Server instance. You connect to the host to customize it for your software. So imagine you're installing something like SharePoint. You can configure it appropriately. And then you connect to the RDS Custom endpoint and run your application as if it's RDS. So on a go-forward basis, it's a fully managed service, but you have the access you need in order to set up your legacy application successfully. And so the benefits this gives you, flexibility. For example, you can bring your own media, you can do custom patching, you can customize the high availability configuration of your database. After that, it's a fully managed experience on Amazon RDS. You can pause, resume the automation, you have automatic provisioning, monitoring, backup, restore, and scale storage of your database. But you also get granular control. So you have host level access, you can decide ownership of resources and control access management to your database. So the flexibility that RDS normally takes away in order to give you a more secure experience, you have now access to set up your application. And so for lift and shift, it allows you to bring your application to Amazon RDS with little to no changes when you have a third-party application you want to bring to RDS. And you can migrate using any of the existing technologies such as database migration service. Now today, Amazon RDS Custom supports two scenarios. Amazon RDS Custom for Oracle uses customer-supplied software, so bring your own media. And Amazon RDS Custom for SQL Server, we supply the software, and you can have your choice of SQL Server Web, SQL Server Standard, or SQL Server Enterprise. Now, the last thing we'll touch on is Amazon RDS multi-Z DB clusters. This is an Amazon multi-Z deployment option that gives you 2 readable standbys instead of 1 passive standby. So as a reminder, why do we do multi-Z deployments? Variety of reasons for high availability. It gives you benefits like system upgrades take place on the secondary first and then get carried over the primary, so it's less disruptive to your primary's workload. There's no load on the primary during those backups. The DB instance endpoint remains the same after a failover, so your application has to pay attention to the failovers. It just has to be aware when the connection's dropped and restored. If there's a failure, the availability duration is limited to the time it takes for the failover to complete, which in multi-Z DB instance today is typically 60 to 120 seconds. And as a result, you get an SLA of a 99.95% uptime agreement for that database instance. Now we've introduced a new deployment option, which allows you to deploy 1 primary and 2 readable standbys across 3 availability zones. So multi-Z DB instance, 2 instances, 2 AZs. This is 3 instances, 3 AZs. And we'll talk about how this works, but this gives you twice the write transaction commit latency, twice as fast. Automated failovers now take typically 35 seconds instead of 1 to 2 minutes. The standby instances are accessible for read-only queries, and you can do read-write splitting because we give you separate endpoints for read-write and read-only. Let's talk about the improved write performance. Benchmarks come in many flavors. Here's just one example. We suggest you try your own. But this is an example of Amazon RDS for MySQL in this deployment using an OLTP read-write workload using Sysbench. And you can see the comparison. The blue curve here is multi-Z with 1 standby, and the orange curve is this new deployment option with the 2 readable standbys. And we typically see around a 2x increase in transactions per second. We also see up to 2.5 times improvement in the P95 of the write performance. And you can see similar performance in RDS for Postgres as well. Now, part of what you also get from this besides improved write performance is also additional read capacity because we give you a reader endpoint. So you still have your primary endpoint where you can do read-write workloads, but there's also a reader endpoint that lets you round robin between the 2 standbys and send read traffic to those as well. So it takes pressure off the primary in this cluster. Additionally, if you choose to want to follow the nodes yourself, there are also individual endpoints for the 3 instances. So if you want to have your application keep track of who's the primary and who are the secondaries, you can do that as well and have traffic shaping. Failovers are also shorter. So what goes on during a multi-AZ DB instance failover? Typically, Amazon RDS detects that there's something wrong with the primary. It triggers a failover, and two things are happening in parallel. One is the database is going through crash recovery. The new primary is restoring the state that the old primary was at, and at the same time, the DNS endpoint is propagating over to the new primary so that your application doesn't have to worry about that. And that typically takes 1 to 2 minutes to complete, and then you're back up again. Now, in a multi-AZ DB cluster, there's no crash recovery step. So that failover time drops dramatically. Typically, 35 seconds is the failover. Now, there's a caveat, which is one of the secondaries becomes your new primary. And if it is lagging significantly behind the primary that failed, it also needs the time to catch up. So you want to pay attention to, do you have a secondary that's staying close to the primary? Usually you do. We have mechanisms in place to keep it close. You can monitor this in CloudWatch, but that is one factor. But if all things are going under typical operating conditions, one of your secondaries is lagging by no more than second or milliseconds behind the primary. So when there's a failover, you typically are seeing 35 seconds. So how does this deployment option actually work? It's different than a multi-AZ DB instance. So we deploy three instances, 3 storage volumes across 3 AZs. In this diagram, the primary is in the center. So you write to your primary, and that primary writes to local storage in the instance. So we use D-type instances in this deployment. And when that primary receives the write, it sends out a request to the 2 secondaries and says, who's got it written to their disk? And the first secondary to call back and say, I've got on my local disk 2, closes the commit. So there's a synchronous loop on at least one of the branches to the left or to the right before the commit is acknowledged back to the application. What that means is you're written in 2 places before the write completes. Then the data is moved asynchronously to the underlying EBS volumes for durable storage. So you're always writing in 2 places. Initially, the local disks. Long-term, you're on the EBS volumes. So when you do reads, unless it's in the memory, it's coming out of the EBS volumes. So it's a hybrid storage system. So if you compare this to multi-Z, you say, well, where does the speed come from? Well, part of it is SSD drives or local disks are faster. But part of it also is fewer network hops. So if you look at a multi-Z DB instance, you write to the primary, which in this case is on the far left. It writes first to the EBS volume. The block gets replicated across the AZ to the secondary instance. It gets written to that second EBS volume. It acknowledges back that it has it on the second volume. The first volume then comes back to the instance and says, I know I've got it in 2 places. So there's 4 steps to close that. On the right, you see we're sending it out to both standby simultaneously, and the first one to come back, say, I've got it, closes the commit. So it's in any one of 2 quorum in Postgres or a semi-synchronous replication in the parlance of MySQL. The other thing that's happening is we're sending smaller packets of data to do this, because on the left, it's block replication. On the right, we're either sending bin log for MySQL or the wall log for Postgres, so there's less data going across the wire as well. So these 2 things, the local disk and the data going across the wire, combine to make the writes faster. So how do you deploy these things? So through a different CLI command. So to create a multi-AZ DB instance, you use create DB instance API action. And you have that field at the bottom that says, give me a multi-AZ instance, and it goes from single AZ to multi-AZ. To create a multi-AZ DB cluster, you actually use the cluster API. You say create DB cluster. And you can see there's a couple of changes. Otherwise, the API action fields are the same. So you specify the identifier of the database. You specify the instance class. You see the difference here is that D. So you have a Graviton instance. R6G is a regular Graviton instance. R6GD is a Graviton instance with local storage. So you provision one with local storage for the cluster. Otherwise, you pick your engine, your version, your usual configurations. But in the case of the multi-AZ DB cluster, you don't say it's multi-AZ, because by definition, it's a cluster. It's going to be multi-AZ. So today, what's supported Amazon RDS for MySQL, we support MySQL 8.0 minor version 26. And on Postgres, we support Postgres 13 minor version 4. And that comes with extensions that are commonly used in Postgres, such as pgcron, pgpartman, and PostGIS. Instance types today, Graviton family, so M6GD and R6GD. These are the M6GD are the general purpose instances with local storage. The R6GD are memory optimized. They have twice the memory per core as the M6GD, but otherwise give you the same instance store and high performance networking. And in this case, the size of the instance store is not that germane because it's only being used for logs. Most of your data is still in the EBS volume, so you don't really need to worry about how big is a local store. We've made sure it's big enough to keep you flowing. And so the instance store that you use with these is an I01 volume. That's SSE storage. They're scalable up to 64 terabytes of data. They give you single-digit millisecond latency, so they're very fast for retrieving the reads. You can provision them for up to 80,000 IOPS, and they deliver those IOPS within 10% of your target performance 99.99% of the time. So great for production workloads. When you look at these resources in the RDS console, they show up as a cluster, so you'll see all the nodes. So if you look at a multi-Z DB instance, you'll see just a single line. This is a DB instance, it's multi-Z or it's single AZ. In this case, you'll see the cluster and you'll see the 3 nodes. And this is in part because you can interact with all 3 nodes. You can take reads from them. You can also monitor how well they're doing. And as I said, there's actually 5 endpoints. There's the managed read-write endpoint, there's the managed read-only endpoint, and then you can directly connect to the 3 nodes yourself. And that's why we give you the visibility into all of them. Finally, migration options. If you want to migrate from an existing Amazon RDS deployment, one option is to create a DB snapshot and restore from a snapshot. So you take your single AZ or multi-AZ instance, make that snapshot, and you can restore from that snapshot using essentially two commands. Create DB snapshot and restore DB cluster from that snapshot. Now, that requires a little bit of downtime because if you have to take down your app, bring up the snapshot, reconnect. If you'd like to do a live migration, then you can use AWS Database Migration Service, and then in this case, have your application communicating with your multi-Z DB instance, have DMS replicating to the cluster, and when you're ready, fail over the application to the multi-Z cluster. And there's a blog talking about how to do a migration with Amazon, a high availability migration with DMS. It's a general purpose blog. We're working on something more specific down the road. So that's the innovations I want to talk about today. We went through that fairly good pace. I'm here for any questions anybody has after the session. If you want to learn more about specific cloud skills, I want to let you know we have Skill Builder and certifications available for folks that want to do the work. Otherwise, my only last request is please complete the session survey, and I'll be at the corner of the stage to answer any questions folks have about any of these capabilities of Amazon RDS. Thank you.